Hello. In this project, I worked on building a deep learning model using CNN, means convolution neural network, to detect whether a person is wearing a face mask or not. This is very relevant real world problem, especially after COVID, where monitoring mask usage in public places like airports, hospitals, and malls become important. So the goal was to build a system that can automatically classifies image into two categories, with mask and without mask. Here you can see in the problem statement. Next, problem understanding. So basically this is a binary classification problem. The input of model is an image of a human face, and the output is either with mask or without mask. Since we are dealing with image data, I used CNN, which is very effective in capturing spatial features like edges, textures, and patterns in images. Here you can see the problem statement of this face mask detection. Next, we move on to dataset. For this project, I used the dataset from Kaggle. After downloading, I explored the dataset structure and found that it contains two main folders like with mask and without mask. Here you can see I have found the two main folders which it contains. Next, I also here you can see use the dataset from Kaggle for this project, and it contains two categories, with and without mask. Next, I also found the directory like two main folders. Next, each folder contains images corresponding to that classes. So the data is already labeled, which makes it easier to use for supervised learning. And then next, I also verified that the data set is properly organized because CNN model requires a clean folder structure to load images correctly in data collection, like in loading the data set. Next, in data pre-processing, we move on there. In data pre-processing, next here. Which is a very important step. First, I resized all the images to 224 by 224 pixel. This is required because neural networks needs all inputs to be of the same size, as you know. Then I normalize the pixel values by here you can see applying the normalization by scaling them between 0 to 1, and this helps the model train faster and more efficient because large pixel values can slow down learnings. After that, I split the data set into training and what we tell uh, training and validation sets. The training set is used to train the model, and the validation set is used to evaluate how well the model performs on unseen data. These steps helps us detect issues like overfitting. Here you can see the test data set. In test data set, it has found that 7,553 files belong to two main classes, which are with mask and without mask. In that using 755 files for validation. What I told before. Next, here I have written what I've done in data pre-processing. Image were resized to 224 into 224 for uniformity. Pixel values were normalized to the range from I have told no like that 0 to 1 to improve model performance. Labels were automatically encoded into numerical format 0 and 1. The data set was split into training, validation, and testing sets, as I told before. Next, we move on to data augmentation. Like to further improve the model, I applied this data augmentation. This includes techniques like flipping, rotation, and zooming. The idea is to artificially increase the diversity of the dataset without actual collection of new image. For example, a flipped image is still the same class, no new classes appear there, but it helps the model learn better general features. This step is very useful in improving generalization and as I told, reducing the overfitting. Here I also make the insights. Data augmentation techniques such as flipping, rotation, zooming were applied to increase dataset diversity and improve model generalization. Uh, these help reduce, as I told, overfitting will be reduced and improves performance on unseen data. Like this, data augmentation is also been performed, and then we move on to model building, like a CNN model building. As I build the CNN model, the architecture starts with convolution layer, where filters are applied to extra features from the images. These features can be edges, textures, or shapes. After each convolution layer, I use the max pooling layer. This reduces the size of the features maps and helps in reducing computation while keeping important information. I use multiple such blocks to allow the model to learn more complex features, like step by step, let it learn like that. After the convolution layer, I flattened the output into single vector. Then I added a dense layer which acts as fully connected layer to combine all the extracted features. Here I also add a dropout. You can see in this model only. Uh, Everything is been there, and also dropout layer which prevents overfitting, as I told. And dropout randomly ignores some neurons during training, which makes the model more robust. Finally, I used sigmoid activation. Here you can see in the last line function in the output layer. I have been used this because this is a binary classification problem now. So that's why it gives an input between 0 and 1 representing the probability of the image belonging to classes. So I also compiled the model here. You can see up to Adam optimizer. I have used Adam optimizer and here in compiling the model. Then I perform the model summary here, where it shows layers and output shapes and parameters. Total parameters appears here, and trainable parameters and non-trainable parameters. Everything is been present here. You can see in this. Next, I moved on to model training. Before model training, see, I also written insight for this also. A CNN model was built using convolution layers, max pooling layers, as I told, and dense layer. Relay activation was used in hidden layers, and sigmoid activation in the output layers. As we done this in previous project also. Dropout was used to reduce overfitting, as I told. Next, after CNN model training, uh, after building the model, I moved on to model training, where in model training, I compiled it using an Adam optimizer, where I showed in compiling the model there. Adam optimizer for compiling the model, which is efficient for deep learning models. For the loss function, I used binary cross entropy. Here you can see, I paste it here. Cross entropy for since this is binary classification task, for loss function I used binary cross entropy. I trained the model for 10 approaches. Here you can see I have trained for 10 approaches. During training, I observed that both training accuracy and validation accuracy were increasing, which indicates that the model is learning properly. Also, the validation accuracy was close to the training accuracy, which means the model is not overfitting, as I told. No overfitting has been occurred here. So I conclude this step by here by telling the model was trained using the training dataset and validated using validation dataset, Adam optimizer and binary cross entropy. Loss functions were used. Accuracy was used as the evaluation metrics. The model was trained for multiple approaches, 10 approaches, I told, to improve performance. Next, after this step, we move on to model evaluation, where accuracy, prediction, and confusion metrics, precision, and recall were performed. In model evaluation, the model achieved around 94 to 95 percent accuracy on the validation dataset, which is good result. I also used the confusion metrics to analyze the predictions. Here you can see predictions has been also done. It shows how many predictions were correct and where the model made mistakes. All were shown here. Most of the predictions are correct with very few misclassifications. And also exact precision and recall values here after confusion matrix here precision and recall values. Precision tells how many predicted positives are actually correct, and recall tells how many actual positives are correctly identified. Both values are high and balanced, which means the model performed well for both classes. And as I told, confusion matrix for prediction was done. Here is the confusion matrix output. So overall, the model performance means the model performed well and can effectively classify images as with mask or without mask. These type of systems can be extended to real-time applications like surveillance system or entry control system. In the future, we can improve the model further by using larger datasets or more advanced architectures like transform learning, like that all. By this, I conclude this project. I also wrote the confusion here. See, the model was evaluated using accuracy confusion matrix at last, and classification report was given. The confusion matrix shows correct and incorrect predictions, while precision and recall provides detailed performance for each classes. Hence, I conclude this here. Thank you.